So I would first like to thank Professor Panigrahi and other organizers for giving me opportunity to speak here, and it's a very interesting meeting, and I can see from this array of very nice speakers. So after this very illuminating talk by Aditi on quantum information and quantum computation, communication, etc., you will have to switch gears and be ready to think about some foundational problem, which is a well-known problem of wave-particle duality. So the plan of the talk is the following. First, I will talk about this two-slit experiment and then how it is related to complementarity, which is also colloquially called wave-particle duality. Then how complementarity is related to entanglement. Then we'll go and discuss the generalization to this n-slit interference experiment. And then we will discuss a new development, which is called wave particle triality. And yeah, then I'll conclude. So first, let us consider a very simple experiment that you have a source and you have a double slit and you have a screen here and you have quantum particles emerging from this source and traveling in this direction. So these quantum particles travel one by one. Not I have drawn them all together, but imagine that they are traveling one by one. So suppose you keep the lower slit closed and only the upper slit open, then only particles which are able to pass through this upper slit, they will land on this screen, and of course you can see because of this some uncertainty, they will all not lie on a point, there will be a distribution. On the other hand, if I close the upper slit and leave the lower slit open and repeat this experiment, you will see that there is again particles will fall on a
हेलो
distribution.
हेलो
तो
Yes,
ताबिश की
please.
वो नहीं अटेंड कर रहा टॉक
ओ हाँ कितने बजे है
अभी स्टार्ट होगी
ओके
Okay, so you will see a distribution which is slightly shifted. So I have drawn the screen close to the double slit. If it is far apart, you will see that these two distributions will be very close and almost overlapping with each other. So one would think that if you let both the slits be open at the same time, then the particle will either pass through the upper slit, then it should fall on this distribution, or if it goes through the lower slit, it should fall on this lower distribution, the second distribution. So there are only two possibilities for this particle. So intuitively, we all think that if both the slits are open, this net pattern should be just the sum of these two patterns. But what actually happens is that if you let both the slits open, you will see a very interesting pattern, which is an interference pattern. You will see bright and dark fringes on the screen, something very different from just a sum of this. So this is a very intriguing and surprising phenomenon. How does it happen? Because we were anyway throwing particles one by one. If the particle is passing through one slit, how does it matter to that particle whether the other slit is closed or open? So this experiment is very surprising, especially when it is carried out with massive particles. So this experiment has also been done. I am reporting here this latest one in 2018. The first one was published in 1989, American Journal of Physics. So you see that these electrons are passing through a double slit and they are falling on the screen. This is the image of the screen. So these impression of each electron landing is represented by a dot. So you can see that they just look like random dots. But as the number of dots keep increasing, you will see slowly an interference pattern emerging. And they fall on this bright fringes, and there are some regions in which electrons almost never fall. So how does one reconcile this? That when the electron we believe is a particle and it should pass through only one of the two slits, how does it make a difference whether the other slit is open or not? So if we try to figure out which of the two slits the particle pass through for each electron, then what happens? So suppose we hook up this kind of a setup that in front of one of the slits we put a small, say I'm just calling it a path detector. It could be a camera which will just take a picture of the particle passing through the upper slit. So for each particle you will know whether the particle passed through the upper slit or the lower slit. But in an actual experiment, we see that as soon as we hook up any such method to find out which of the two slits the particle passed through, the interference pattern disappears. And we are left with a pattern which is just the sum of the first two patterns which I showed. So this is a very interesting problem, that as soon as you try to find out which of the two paths the particle took, the interference disappears. If you don't know which of the two paths the particle passed through, then you get an interference pattern. So Niels Bohr was so intrigued by this phenomenon that he elevated this to a new principle of physics. He called it the complementarity principle. So in 1928, he said that certain physical concepts are complementary, and if two concepts are complementary, an experiment that clearly illustrates one concept will obscure the other complementary one. For example, an experiment that illustrates the particle properties of light will not show any of the wave properties of light, and vice versa. An experiment that illustrates the wave property of light will not show any particle nature of light. So in this two-slit experiment, the which way information if you get, that is like particle, the particle is behaving like a particle, the electron is behaving like a particle because it is passing through a particular slit. And when you see interference, because interference, we already know that we identified with the wave nature of light, Young's double slit experiment. So if you see interference, then it represents the wave nature. So what this complementarity principle says that either you can see wave nature or you can see particle nature at the same time, but not together. They can all be observed at the same time in the same experiment. So Einstein was, he did not believe this principle, and he actually came up with a thought experiment which he believed that it sort of disproves this complementarity principle. So this is Einstein's famous recoiling slit experiment. So you can see, as in the previous figures, there is a double slit sitting here and then there is a screen, sorry. But before this double slit, each particle is passing through a single slit, which is very light and movable. So I have drawn these rollers here to show that in this direction, let me call it the X direction, and this is the Z direction along which the particle is traveling. So in this X direction, the slit is free to move, so it can even move if a single particle hits the side of the slit. So you can see that if the particles are going in the straight line, now if it changes direction and goes through the upper slit, that means it would have gained some momentum in this positive X direction. And this momentum, where would this momentum come from? It would come from the recoil of this slit. So this slit, by momentum conservation, this slit should experience a equal recoil in the opposite direction. So if the particle goes through the upper slit, the single slit should recoil in the lower direction, and if the particle goes through the lower slit, it should recoil in the upper direction. So Einstein believed that this momentum of the slit, which you can measure after the particle has passed through and landed on the screen, you can measure the momentum of this single slit, and this will give you the which way information. So he believed, Einstein argued, that you will be able to see interference, and you will also be able to find out which slit the particle passed through. So this was proposed in this famous Solvay conference in 1927, and you can see this group photograph of this meeting, and you can see that most of them are actually Nobel laureates. This is Marie Curie sitting here, Einstein sitting here, and this is Niels Bohr here. This is Schrödinger. So Bohr was very unhappy with this, and he right away he could not come up with a solution. So, but he went back, and next day he came up. I will not go over this. So next day he came to the conference, and then he gave his reply. So what was Bohr's reply? So Bohr's reply was that if the single slit is so light that its experiences are recoiled from a single particle passing through, then it should be treated quantum mechanically. So suppose the difference in the momenta of the particles in the two slits is P1 minus P2, and you can see this setup. So in this setup, this momentum will be given by 2p sine theta by 2, where p is the momentum in this direction. And if theta is very small, if this screen is double slit is far away, this theta will be very small, so it can be approximated as p theta, and p will be h by lambda by de Broglie's formula. So, and theta will be approximately given by d by L. D is the separation between these two slits, and L is the distance between this slit and the double slit. So for simplicity, these two separations are made to be equal, but they can be unequal also. So basically this should be the difference between the momenta of the particle when it is passing through the upper and lower slit. So same recoil momentum should also have this recoil of the slit in two situations should also have the same difference. In order to measure the recoil momentum of the slit, it should be measured by at least as accurately as delta px equal to, so let us say, so this is the difference, where let us say 1/4 is the accuracy. So I can be more accurate than this, but let me just say that I am saying 1/4 of this should be the accuracy of this. So position of the single slit is uncertain by at least by an amount. So now by this by this uncertainty principle, if this recoiling slit has this uncertainty in momentum which is equal to this, its position of the single slit will be uncertain by this h cross upon 2 delta px, or basically delta x will be equal to lambda L upon pi times d. So now if this slit is slightly brought lower, then this interference pattern also shifts slightly in the upward direction. If this position of this single slit is slightly in the upward direction, this interference pattern also shifts slightly in the lower direction. So if the position of the single slit becomes uncertain, position of the interference pattern will also become uncertain. So the position of a fringe is also uncertain by an amount delta L by pi times d. But you know from this Young's double slit experiment that the separation between the two neighboring fringes, the fringe width is given by lambda L upon d. And you see that this is of the same order as the uncertainty in the position. So interference pattern will be washed out. This was Bohr's reply, that because of this uncertainty principle, the interference pattern will be washed out. You will not be able to see interference. So Einstein that time accepted this explanation. So what is the implication of this Bohr's resolution? So the first one seems to be that uncertainty principle seems to be enforcing complementarity. And after that, many people over the years have come to believe that complementarity is, in some sense, a hidden restatement of the uncertainty principle. So people believe, what is the origin of complementarity? They believe that getting which way information will necessarily disturb the state of the particle, and disturbing the state, that disturbance will be enough to wash out interference. So the implication seems to be that uncertainty will sort of disturb the particle, and that is why the interference pattern will be washed out. So that time it was just a thought experiment, but now with the advent of technology, this experiment has been realized in various ways. In 2007, this was realized by a trapped ion realization. So this trapped ion was treated as a recoiling slit. Then this again 2001 paper, and this Hiroshi's group who got a Nobel Prize in 2012. Then still much later, more experiments have been done to realize this. In this one in 2013, and this one I think later 2014. So this experiment has been realized, and these people have noticed that this interference pattern actually is washed out. Now let us ask this question: is uncertainty principle a requirement for complementarity? Could Bohr have replied to Einstein without invoking the uncertainty principle? So for that, let me first take you, give you a brief review of what a quantum measurement is, according to von Neumann. Von Neumann was the first one who formulated theoretically what a quantum measurement should be. So according to Neumann, a quantum measurement consists of two processes. Process one is a unitary evolution, which establishes correlation between the system and the detector. What does this mean? That if suppose you are measuring a spin half, whether spin is up and down, so your measuring device, suppose it is a pointer, the pointer should have at least two directions. One direction will point to the upspin, and the other direction of the pointer will be correlated to the downspin. That is the meaning of correlation. So if the system initial state is in a superposition of many states, so suppose the initial state of the system which is being measured is like a superposition of this many states Ci, and detector is initially in a known state D naught. So the initial state of the system and the detector is given by this product. This unitary evolution, which is the process one, this turns it into an entangled state. So now this is a correlated state, an entangled state. Corresponding to every psi I, there is a different state of the measuring device. This is a detector state. So for example, for psi1 there will be D1, psi2 there will be D2, and so on. So it becomes a superposition of this many states. So it essentially becomes an entangled state. So second process is a non-unitary one, which picks out a single result from this superposition. So this is a superposition, still a superposition of many possibilities. Process 2 is what? From superposition, it picks out randomly one of the outcomes. So for example, you might get psi k, and the detector will be thrown into the state dk. And this will happen with a probability ck mod square. These c's are sitting here. So this process 2 is what constitutes the measurement problem, and this process 2 is something which is still not understood clearly how it happens. So we will not be bothered with process 2, we'll be bothered just about process 1. So now in this Einstein's recoiling slit experiment, since the recoiling slit is measuring the path of the particle, how does this von Neumann's measurement process apply to this Einstein's recoiling slit experiment? Two orthogonal states of the particle are psi1 and psi2, corresponding to the psi1 going through the slit 1 and psi2 particle going through the slit 2, and two momentum states of the recoiling slit P1 and P2. So so that means if the particle goes through the upper slit, its state will be psi1, and the recoiling slit will have a state P1, and if the particle goes through the slit 2, the recoiling slit will have a state P2. So the point to be noted is that two different momentum states of the recoiling slit necessarily get entangled with the states of the particle passing through the two slits. So this entangled state will necessarily be created. This is just a result of this von Neumann's process 1, that if this recoiling slit is to measure the path of the particle, there has to be this entangled state created. Other important point is that in principle it is possible to find an interaction which will not affect the states of the particles psi1 and psi2. So suppose without this any entangled state, the states corresponding to particle going from slit 1 and slit 2 would be psi1 and psi2. So this effect of the recoiling slit may not be to disturb this psi1 and psi2, it is just to create this entangled state. So psi1 and psi2 are not modified, but only the entangled state will be created. So this point was not part of board's reply, and I will just show you that this is enough to rule out interference. So first, without which way information, if the particle is passing through the two slits, it will be just a superposition of psi1 and psi2. What is the probability of finding the particle at any point x on the screen? You just take a mod square of this. You will get a psi1 mod square, psi2 mod square, and then there will be these cross terms. So these cross terms are what represent interference. Now, if you have the which way information present, if the recoiling slit gets which way information, then your state will be this entangled state. Now, similarly as before, you can try to calculate the probability of finding the particle at any position on the screen. Just take a mod square. Again, you will get a mod square, and then the difference now is that this interference term now has this inner products of P1 and P2 sitting here. And if P1 and P2 are these momentum states which are orthogonal, that means which can be distinguished without any problem, then this interference term becomes 0, and you are just left with a pattern which does not show any interference. So interference is still by the orthogonality of P1 and P2. So that means just by the fact that the recoiling slit has stored which way information, it destroys interference. You don't even need to read out this information. Just storing the which way information in this detector states is enough to kill interference. That is an important lesson. So you see that if this entanglement between the particle and the recoiling slit had been recognized and its implication understood, Bohr could have provided a simpler rebuttal to Einstein. So why did this not happen? Because all this discussion was going on in 1927, and this concept of entanglement was introduced only many years later in 1935 by Schrödinger. Now, can we make this argument more quantitative? So suppose you have a a particle, quantum particle. For short, I will call it a quanton. It is passing through a double slit. And so the state is given like this. Density operator you can write just as an inner product of this state, like this. So you can define the fringe visibility as this. On the screen, in optics, there is a very simple way of defining visibility of interference. Maximum intensity minus minimum intensity around one small region divided by the maximum intensity plus minimum intensity. So this is called the fringe visibility. So this is actually a measure of the wave nature. If you see interference, then visibility will be maximum. If you don't see interference, this fringe visibility will be 0. Now, next thing is that we want to get the particle nature, which slit did the quanton pass through. So suppose we know that the quantum is more likely to pass through one of the particular slits. Suppose this is unequal probability. That means this C1 and C2 are not equal. So this idea was first proposed by Greenberger and Yassin. So they say that if the probability to pass through is unequal, then you can define a predictability like this. It is just the difference between the two probabilities. And then with this visibility, you can actually show that P square plus this V square is less than equal to 1. So this was the first quantitative statement of Bohr's complementarity principle given by Greenberger and Yassin. But here you see that if these two probabilities are equal, then this predictability is 0. So this doesn't address the problem where these two particles are particle is equally likely to pass through the two slits. So then we have to go to the second scenario, where these two particles may pass through the two slits equally or unequally, but you have a path detector in place. In the previous scenario, there was no path detector here. So now there is a path detector. So this thing I have already explained. So this problem was dealt by Englert in this very famous paper in 1996. So he introduced a path distinguishability, and this by D, which was based in this minimum error discrimination. So now the problem of distinguishing, finding out which path the particle followed boils down to distinguishing between these states D1 and D2, path detector states. So if you can distinguish between the path detector D1 and D2 states, then you can tell very easily which slit the particle passed through. So he shows that with this visibility and this distinguishability, they follow this duality relation, and this became a very famous wave particle duality relation. D square plus V square is less than equal to 1. So this is essentially a quantitative statement of Bohr's complementarity principle. So now we take a slightly different approach from this. Again, we deal with the same problem. So now here you see that this minimum error discrimination has this small problem that there will always be some error. If these two states D1 and D2 are not orthogonal, there will be some error. That means you might be able to predict that particle pass through a particular slit, but in the end your answer may be actually wrong. So, but it tries to minimize that error. That is the minimum error discrimination. So we define a new distinguishability which depends on this unambiguous quantum state discrimination. There is another method. I don't have time to go into the details. You can read up about this on your own. The difference is that here there is a new way of measuring these two states. If you are given a state, then to find out whether the state is D1 or D2, there is a way in which you can distinguish between these two without any error. You can unambiguously distinguish. But the caveat in this method is that sometimes randomly this method will fail. But when it fails, you will know that it has failed. So either you fail, but when you succeed, then you succeed without any error. That when you succeed, then you will know 100% for sure that the particle passed through a particular slit. So we define this, our distinguishability D, as the maximum probability with which D1 and D2, sorry, this should be D2, D1 and D2 can be unambiguously distinguished. And visibility we take the same as the conventional visibility. Using this, we have shown that a simpler linear duality relation emerges. dq plus v is less than equal to 1. This work was done in this. So now you can contrast this with, compare and contrast this with Engler's duality relation, which is a quadratic relation and which is this linear relation. Now you might ask, what is the advantage or disadvantage of these two relations? So that time we did this, we ourselves were not sure what is the advantage or disadvantage of these. But in this paper by Franco Nori's group, incidentally Franco Nori was here and he gave a talk in this forum last week. His group carried out this experiment to probe, to study this problem, that in this two quadratic and linear duality relations, how do they perform? They did this focused experiment and their conclusion was that linear duality relation is actually tighter than the quadratic duality relation. Okay, so now let us ask further question that if this wave particle duality and complementarity holds for a double slit experiment, it should also hold for a triple slit experiment and a four slit experiment, in general for a n slit interference. So people also thought that, and there was a considerable effort put in that direction, and a lot of this work was done, but people were simply not able to derive a duality relation for this n slit interference. A lot of effort was put in. So why it was so difficult to do that? So Engler's approach for this two slit was that initial state of the Which-Way detector is this D0, D under this in outer product of this initial state. When the particle goes through the upper slit, then this state of the path detector is this. If it goes through the lower slit, state of the path detector is this. His distinguishability is this. Basically, this is quantum information, people will recognize this as a trace distance. He defined it as this. And it turns out to be this expression, square root of 1 minus mod of the inner product of D1 and D2 squared. Now, from this expression, also you can see that since it depends on trace distance, it is not obvious how to generalize this, for example, for 3 slits or n slits. So our approach is to again do the same thing, use this unambiguous quantum state discrimination. So for example, if we have 3 slit experiment, your problem of finding out whether the particle pass through the slit 1, slit 2 or slit 3 will be just to be able to distinguish between these detected slits D1, D2 and D3. So the problem of finding which slit the particle went through is reduces to problem of distinguishing between these 3 states or n states. So for n states, it will be distinguishing between n states. Now this unambiguous quantum state distribution has been generalized to n non-orthogonal states also, that if you have n non-orthogonal states, and each, for example, state dk occurs with a probability pk, then the probability to unambiguously find out which of the n states is a given state. Suppose you have a state which is given to you, and you have to find out which one is it out of these n states. So the maximum probability is given by this. So this upper bound was found by somebody in a very nice work. So we will just use this result. So probability to, for example, for 3 states, this expression will give you this simple expression. So this is what we can use for our distinguishability. So for this n-path interference, we define a distinguishability for this n-path interference simply as this. So this is basically just maximum probability of unambiguously distinguishing between these states d1 to dn. For visibility also, calculation of visibility is difficult. So for people, for those of you who have actually looked at multi-slit interference, you will know that a double-slit experiment just have maxima and minima. But multi-slit interference patterns, they have primary maxima, then secondary maxima, and so on. So things are not easy, and people have shown that visibility itself is not a good measure for the wave nature. Visibility in many situations can give you a very misleading answer. So visibility also will not work. So fortunately, in recent years, in 2014, this definition of quantum coherence was introduced by Plinio and his collaborators. So that means if you are just given a system and whose state is given by a density operator rho, then you just take the off-diagonal elements of the density matrix, take a mod, and just sum of them, and very simply that is shown to be a good measure of coherence. But here it is not normalized, minimum value 0, but maximum value is not fixed. So what we can do is we can just normalize this and use it as a visibility. So we introduce a quantity which we call coherence, and by introducing this constant, we make this normalized. So this becomes a coherence which is bounded between 0 and 1. So you can check that for a state which is a equal superposition state, which is the maximally coherent state, this C turns out to be equal to 1. For a completely diagonal density matrix, this coherence will be 0. So coherence can be a good measure of wave nature. So now we are in a position to explore this wave particle duality for n-path interference. So now distinguishability we can write for this. So this is now the state for a particle passing through n slits in the presence of a path detector. So path detector gets correlated with the different parts of the particle. So the distinguishability you can write as this, and coherence you can write as this. You take a trace over the detector states. What you are left with the reduced density operator of the particle. Just take the off-diagonal elements, and you don't need to go into the details. Just go into the mathematics. Just believe me that this is the result you get. And from these two, it very simply turns out that dq plus c is just equal to 1. So this was the first duality relation, and because of this equality, this is actually tight. For a pure state, it will always be an equality, not an inequality. It can also be shown that this can be rewritten if you, instead of this dq, if you write this introduces parameter d square as dq into 2 minus dq, then this also becomes a quadratic form. D square plus c square is equal to 1. So this turns out to be the most general formulation of the complementarity principle. It will work for n slits, it will also work for 2 slits. So now the situation is the following. Now we have two kinds of wave-particle duality relation, one based on predictability by Greenberger and Yassin, and this other one which is a quadratic one, the two-slit one derived by Engler, and this other n-slit one derived by us. We have these two situations. Here you have path predictability as the defining the particle nature. Here you have path distinguishability defining the particle nature. Now you may ask, how are these two duality relations connected? What is the relation between this predictability and distinguishability? So this is a question we explored in a very interesting and work which was very exciting for us. This was done in collaboration with Professor Panigrahi, who is the organizer of this meeting, and his students. So I will just not go into the details because I don't have enough time. I will just give you a brief overview of what we did. Visibility is defined as this. So you can see that it looks like a coherence. It is a sum of I not equal to j. It looks like a sum of these off-diagonal elements of the density matrix, but you see it is not just the sum of these off-diagonal elements, it's sum of the squares of the off-diagonal elements. So this is called the Hilbert-Schmidt coherence. So we were able to show that this is actually constitutes a good visibility. That is a that's a different work, and it requires a lot of effort to show that there are many objections which people had to visibility, they will actually be overcome by this visibility. So this visibility turns out to be a good visibility. And this is a predictability which we define for this n-slit interference. For if you take n equal to 2, meaning for two-slit interference, it becomes the same as the predictability given by Greenberger. And there is a interesting parameter I concurrence. I concurrence is what? I concurrence is a measure of entanglement. So we introduced a normalized quantity based on this I concurrence. So entanglement between what? Entanglement between the particle and the path detecting device. So remember I had told you many slides back in the beginning that entanglement plays an important role in this complementarity. Here now it has, and this was never to be seen in any of these duality relations. There is no entanglement occurring here. But here you see that we have introduced this entanglement between the particle and the path detector. And one can show that these three quantities, predictability, entanglement, and visibility, they follow a tight triality relation. So now instead of a duality relation, we have a wave-particle triality relation. So you see that if there is no path detector, that means then there will be no question of any entanglement between the particle and the path detector if there is no path detector. So this entanglement will be 0. If this E is 0, then we will just get the p square plus v square equal to 1, just this Greenberger's duality relation. And if this p square plus e square is treated as equal to d square, then it gives you the other duality relation related to distinguishability. So this also tells you what is the connection between distinguishability and predictability. First of all, this connects both these duality relations. It also tells you that distinguishability and predictability, they are actually connected to each other by entanglement. So this was a very satisfying work for us. And incidentally, this triality relation has recently, in 2025, it has been experimentally verified by this group, published in this journal, Light Science and Application Natures group. So they have explored this wave-particle entanglement triad, another word for triality, in experimentally, and they found it to be nicely satisfying. So now we just conclude. Wave nature and particle nature, initially both thought that they cannot be seen at the same time. But here now it is that scenario is slightly modified, that wave nature and particle nature can be seen at the same time, although to a limited degree. So now you can ask how much of wave nature you want to see, that will limit how much of a particle nature you will be able to see. So if you want to see 100% particle nature, you will see zero wave nature. If you want to see 100% wave nature, you will see 0% particle nature. But partially, you can see both these natures. So for M-slit interference, the wave nature is quantified by quantum coherence. And incidentally, this I didn't have time to go through this. Quantum coherence can also be measured in interference experiments. And that's a separate problem to show that how this quantum coherence, which is defined only in terms of the off-diagonal matrix elements, experimentally how it can be measured in interference experiment, that has been shown and that has also been experimentally demonstrated. So that duality relation is very simple. Now entanglement plays a fundamental role in this interferometric wave-particle duality. And these are the papers which you might look at if you want to further study the subject. Thank you for your attention. Hello.
Yeah, thank you for a very interesting and informative talk. So I have one question.
Yes.
So allow me to ask, what if you consider squeezed vacuum state as an input, and what kind of changes you may expect?
Initial squeeze state may be interesting, but when it goes through the double slit, that information is completely lost. What was the initial state? It will just after when the particle, or say the photon, for which squeeze states are mostly used, when the photon comes out of the double slit, then it will just become a superposition of two wave packets, two specially separated wave packets. So all that information about whether it was a squeeze state initially or it was a different state, that might be completely lost.
Okay, and same regarding thermal state. So if you consider thermal state, will you see some different or I mean path distinguishability and visibility? Will you see some different results?
Yeah, that's an interesting point. If there's a thermal state, so distinguishability will not be affected, but visibility will be affected because the coherence will be affected. Because if it is a thermal state, the two wave packets which come out of this double slit, suppose we just have two slits, it may not be a pure state superposition of two-way packets. It might be a mixed state, depending on how strongly is this thermal effect is. So it will affect the visibility. So then it will no longer be an equality, it will be an inequality.
So did you study that one, or
Yes, that has been studied.
Okay, good. Thank you.
Yes.
I have a question. So in this n-slit setup, so coherence act as a resource, and the entanglement is not act as a resource for this. So it helps to helps in state discrimination problem. So so the role of entanglement. So we don't need entanglement. It is not as necessary for this problem.
But for distinguishing between the different parts, we need entanglement. The coherence, although it's a resource, it will give you no information about which slit the particle went through.
Oh, and so the role of this, if you use the path coherence as a measure, so the role of path coherence is come for the state preparation type of things, and the role of entanglement comes from the measurement side.
Yeah. So actually, I think what you are hinting at is that from how you can understand this wave particle duality from an information theoretic point of view. There has been, yeah, that's an interesting problem, and some people have actually studied that. You can maybe look up the literature. That people have studied this complementarity from a information theoretic point of view. That if you consider this entanglement as a resource and coherence as a resource, then what does this duality relation mean, and so on.
So, thank you.
Okay, sir, I have few questions. Yeah. So my first question is, what is that? I want to know the initial state that you considered when you considered quantum with the detector, whether that is a mixed state or the pure state.
No, that is a pure state.
That is the pure state. And for the for n-state case, the concurrence you have defined, can we apply it for mixed states as well, or just for pure states?
Yeah, it can be done for mixed state also. We have in the paper you can see that we have dealt with the mixed state problem also.
Okay.
The only thing is that when you deal with mixed states, then this equality becomes an inequality.
Okay.
Yeah, so this equality becomes a inequality.
Okay, then suppose if we take a mixed state and we get a tight triality relation, then what can it impose? Suppose there is a situation where we started with a mixed state and we ended up in a triality relation, then what will it imply?
No, you will get a triality relation, but you will not, this sum will not be equal to 1. It will be less than 1.
Okay.
Yeah.
Okay. Thank you.
So this triality, this sum will give you 1 only for pure states. For mixed states, it will give you a number less than 1.
Maybe I am thinking Mach-Zehnder interferometer. Maybe you can do this experiment, and then maybe we will see some different kind of changes. So
yeah, for Mach-Zehnder interferometer also, it should follow the same thing, because here we have not specified whether it is a slits. You just psi1 and psi2 were just two parts. So it should apply to Mach-Zehnder interferometer also.
yeah, I'm just thinking. Good. Thank you.
So, Professor Qureshi, thank you for this very insightful and interesting talk. So we have learned a lot, and I hope the participants have learned and motivated to pursue some of the research work on this direction. Professor Simanchal has some question, but due to some technical issue, I'm not able to take this question. So thank you, Professor Qureshi, for your time from your busy schedule. And thank you very much. So
thank you.
Yeah, we conclude.
So if anyone has a question, you are free to email me also. I'll be more than happy to answer your questions.